All right. Today we have more inverse trig functions, the remaining three. We learned the inverse trig of sine, cosine, and tangent. So we'll learn cosecant, secant, and cotangent today. But first, let's start with some fun problems. So here we have find the exact value of sine of the inverse tangent of 1/2. Okay, so I'll show you how to handle these. We do this by making a substitution. Okay. Why is that wheel on my screen? You guys see that too? That blue wheel?
Yeah, I see it.
I don't see it. No, I'm just kidding. I do see it. I'm trying to mess
It's
with you.
there.
It's Pac-Man.
It's Pac-Man. Let me change the screen. Let's see if it changes. Go away, blue wheel. All right, good. Whatever that was. All right. Okay. So to handle these, we make a substitution. So we'll say, again, let theta equal the inside of the parentheses. So the inverse tangent of 1/2, we're going to let theta equal that. And then, of course, you apply the inverse to both sides. And you get then tangent theta is equal to 1/2. But this can only be possible on the inverse tangent restrictions. Anybody remember the restrictions for the inverse tangent function?
Negative pi over 2 to pi over 2.
Good.
It's the same as sine, except for it can't be equal
Good.
to it.
Same as sine. So this means that now we are going to draw the unit circle where the inverse tangent function lives. Here's negative pi over 2, and here's pi over 2. Well, if tangent is positive 1/2, are we in the first or fourth quadrant?
First.
We are in the first. So here's where we're going to put theta. And if tangent is 1/2, this means that the height of the triangle is 1 and the base of the triangle is 2. This means our hypotenuse is what?
Square root of 3.
5.
5.
Whoa.
Square root 5. Because it's 1 squared plus 2 squared, and you
Oh,
square root
plus.
that.
Yeah, plus.
Right?
I did minus in my
There
head.
you go. Okay. So now theta holds all of this information. So theta is the inverse tangent of 1/2. So this whole triangle belongs to theta, which means we go back to our substitution. So we look back at our substitution, which we made up here, and the sine of the inverse tangent of 1/2 just becomes the sine of theta. And theta contains all this information. So what is the sine at that value of theta?
Well, square root of 5 over.
Good. Square root of 5 over.
Wait.
5.
5.
Yeah, 5.
Because sine puts opposite over hypotenuse. And 1 over the square root of 5 has to be rationalized. So that's how we handle these trig expressions. Any questions on that?
It's fun.
So for the substitution, you're basically going to put theta in place of the inverse.
Whatever, exactly. Whatever function's in there. And then graph it on its restrictions, put it in the appropriate quadrant, and then go back to the substitution and answer the question. Okay. Again, cosine of the inverse sine of negative 1/3. All right. So again, let theta equal the inverse sine of negative 1/3. Then compose both sides with the inverse. And you get sine theta equals -1/3 on what restrictions?
Negative pi over 2 pi over 2.
That's it. Now draw your unit circle. There's negative pi over 2, 0, pi over 2. And if sine is negative, are we in the first or fourth quadrant?
Four.
Fourth. There's theta, and sine puts opposite over hypotenuse. So the length is going to be -1. I mean, sorry, the height is -1. And what is the hypotenuse?
3.
3, which means the base is going to be what?
Square root of 8.
Which is
2 radical 2.
2 radical 2.
So for finding out which quadrant you're in, is there a trick to it, or do you kind of just gotta try and memorize that chart back from last chapter?
From the last section, yeah. If you just know the restrictions, then you'll know what quadrant you're in. Because remember, the inverse functions live in certain quadrants.
No, but I meant like if sine's negative, like is there a little faster trick to remember that, or is that just the chart thing?
Well, where's y negative at?
Okay, the bottom part.
Got it? Don't make it more difficult than it has to be. Okay. All right. So then we come back to this substitution, and you'd get cosine of theta. And what is the cosine at this value of theta?
2 square root of 2 over 3.
2 square root 2 over 3. There it is. Yeehaw. Any questions on that one? Okay. Again. Here, let theta equal the inverse cosine of -1/3. Then you'd have cosine theta equal to -1/3 on what restrictions?
Negative pi over
Negative
2.
square or negative or 0 to pi.
0 to pi.
Mhm.
Those are the restrictions for the inverse cosine, right? Oh, I wrote too big. Oh well. And then here's 0, here's pi over 2. And if cosine is a -1/3, are we in quadrant 1 or in quadrant 2?
2.
2. There's theta, and cosine puts adjacent over hypotenuse. So what would the height be?
2 square root of 2.
2 square root of 2. Come back to that substitution, and you'll get the tangent of theta. And what is the tangent of this value of theta?
2 square root of 2 or negative 2 square root of 2.
-2 square root of 2. Opposite over adjacent. All right. Everybody good with those?
Yeah.
Know those inverse restrictions. Cool. All right. Now here's a tricky one. It almost looks like those, but it's not. Those were cosine of an inverse, tangent of an inverse. This is the inverse of cosine. So this says the inverse sine of the cosine of 5 pi over 6. So for this one, you are going to look at your unit circle and find what is cosine at 5 pi over 6.
Negative square root of 3 over 2.
Good. Yeah, I mean, you can even make a substitution if you wanted. you'd have the cosine of 5 pi over 6, and theta would be negative square root 3 over 2. Which means, coming to your substitution, you'd have the inverse sine of the negative square root of 3 over 2. Okay. Well, where does the inverse sine live?
Negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. So for this one, you would reference the unit circles we made last class, and you would spit out to me a radian value. Since this is a negative square root of 3 over 2, are we in the first quadrant or the fourth quadrant?
We're in the fourth quadrant.
Fourth quadrant. And where, at what radian value is sine negative square root of 3 over 2?
Negative pi over 3.
Negative pi over 3. So this means that the inverse sine of negative square root of 3 over 2 would become negative pi over 3. Boom. Definitely different.
Yeah, that one's kind of weird.
Yeah. So that one just says calculate the value inside. No triangles needed because it wasn't an inverse on the inside, right? So you just go to your regular unit circle, find the cosine of 5 pi over 6, and then you'll get the inverse sine of negative square root 3 over 2, which then you'll reference your inverse unit circles and output a radian value. Tricky, tricky. All right. Any questions on that page? That was fun, right?
Yes, sir.
Okay. So now let's learn about the inverse secant. All right. So here we've done all the work, or I've done all the work for you to save us lots of time. Instead of going through everything that we did last class, we know how it works. Secant's not one-to-one, because if you draw a horizontal line through it, you'd intersect it many times. So we will restrict the domain of the, did I say cosecant or secant? This is secant, right? Sorry, secant. Okay, same thing. So secant, and if we restrict the secant function's domain, we make it a one-to-one function. Well, the domain that we restrict it to is from 0 to pi. If we restrict its domain from 0 to pi, we end up with this graph, where if you were to draw a horizontal line through it anywhere, you'd only intersect it once. Therefore, secant is now one-to-one, which means secant will have an inverse. Okay. And the domain of secant is from 0 to pi, but pi over 2 is not included, because what exists at pi over 2?
Asymptote.
Asymptote. Good. And then the range is from negative infinity to negative 1, and then 1 to infinity. So the secant function shares the same domain as which other one that we've learned so far? Who else has a domain from 0 to pi?
Cosine?
Cosine. Good. The only difference between them is that you can exist at pi over 2. Okay. So then if you find the secant by the compositions and all that fun stuff, we end up with the inverse secant function. And remember that your domain and ranges will switch, right? So now the domain of the inverse secant function is negative infinity to negative 1, union 1 to infinity, and the range is now 0 to pi, where y cannot equal pi over 2. So here is the graph of the inverse secant function. Okay. So our biggest takeaway is just remembering your domain and range, mainly your range. We know that the range deals with the unit circle, so we want to know where does the secant function live. So we'll draw that right below. So here is 0. Here's pi over 2. Here's pi. We don't exist at pi over 2. But the secant, just like inverse cosine, lives in quadrants 1 and in quadrants 2. So again, your values are pi over 6. That's probably too high for pi over 6. There we go. Pi over 6, pi over 4, 2 pi over 3, and then, not 2 pi over 3. I was getting ahead of myself. Pi over 3, 2 pi over 3, 3 pi over 4, and 5 pi over 6. So that's where your inverse secant function lives. Everywhere in the first and second quadrant except at pi over 2. All right. Any questions on that? Not bad, right? Okay. Next is the inverse cosecant function. So just like all our other trig functions, cosecant is definitely not one-to-one. If I drew a horizontal line through it, I'd intersect it many times. So in order to make it one-to-one, we restrict its domain. And we will restrict it from negative pi over 2 to pi over 2. But we cannot exist at 0. There it is. There's the domain of the restricted cosecant function. And then the range is just like secant, negative infinity, -1, 1 to infinity. So if we restrict its domain, it becomes one-to-one. And this is what our domain restricted cosecant would look like. If I drew a horizontal line through it anywhere, I would only intersect it once. Okay, which means, of course, if it's one-to-one, it has an inverse, which is given by the inverse cosecant function. And remember, for your inverse, your domain and range switch places. And again, just focus on the range because it deals with the unit circle. Our range is from negative pi over 2 to pi over 2, where y cannot equal 0. So here is a graph of your domain restricted inverse cosecant function, or just your inverse cosecant. Okay, and notice the, I guess, comparison. What other functions, what other inverse functions share the same range?
Tangent and sine.
Good, tangent and sine. The only difference,
because you can equal negative pi over 2 to pi over 2, just not the 0.
Yeah, good. So very similar to inverse sine and inverse tangent, but remember tangent's not included, sine it's included, but here the only value that's not included is when y is equal to 0. Okay, so let's see where the inverse cosecant function lives. Here's our unit circle. And we have negative pi over 2, 0, and pi over 2. We can't exist at 0, but we can exist at pi over 2 and negative pi over 2. So we know these radian values. Pi over 6, pi over 4, pi over 3, negative pi over 6, negative pi over 4, and negative pi over 3. Perfect. And Those are all the properties of the inverse cosecant function. All good?
Yes, sir.
So kind of easy because we see a lot of similarities with the other ones. So not bad. Okay. And of course, last is the inverse cotangent function. So there's cotangent. Of course, it's not one-to-one. If I draw a line through it, a horizontal line through it, we intersect it infinitely many times. Okay. So if we restrict the domain from 0 to pi, we make cotangent a one-to-one function. So the domain is from 0 to pi not included because, of course, at 0 and at pi, you have vertical asymptotes. The range is from -infinity to infinity. Okay. So here's the graph of the domain restricted cotangent. If I draw a horizontal line through it, I only intersect it once. Therefore, it has an inverse, and your domain and range switch places, and the range is from 0 to pi. The domain's all real numbers. So here is what the graph of your inverse cotangent function looks like. And once again, let's show where it lives. So this lives from 0 to pi. Just like what other function?
Secant.
Secant and cosine.
Cosine. All right. But we can't exist at 0 and pi. So here's 0. Here's pi over 2. Here's pi. So we can't use 0 and we can't use pi. But we can use everything else. Pi over 6, pi over 4, pi over 3, 2 pi over 3, 3 pi over 4, 5 pi over 6. And there you go. Those were the remaining properties of the inverse cotangent, secant, and cosecant. All right. Now let's have some fun again. Next page. Using a calculator. All right, this is going to get crazy though. Okay. So if you don't have a fancy schmancy calculator, then you don't have buttons for inverse secant, inverse cosecant, and inverse cotangent, do you?
So 1 over cosine or negative or in cosine inverse.
Nope.
No, you're not going to use the 1 over, right? Because that's reciprocal.
Oh wait.
Well, he's saying, I know what he said first, like 1 over cosine, but remember that's secant, right?
Well, 1 over. I said 1 over cosine.
And then,
inverse.
and if you did 1 over inverse cosine of x, that's nothing. That's 1 over inverse cosine of x. So it's a good thought. It's a good thought to have, right?
Right.
So this means that in order to calculate these type of expressions, we need to create formulas for it. Oh, this is going to be a good time. So, and if you have the inverse secant button on your calculator, lucky you, you still got to do this work. All right. So it all starts by making substitutions, of course, right? So we let theta equal the inverse secant of 3. Okay. Then, again, compose both sides. Then secant theta is equal to 3, but on what restrictions?
The 0 to pi, where pi over 2 is not.
Good. All right. So this is on 0 to pi, where x can equal pi over 2, right?
Yes.
Okay. All right. So what we want to know is what other inverse functions share these restrictions?
These exact restriction. Oh, just that one.
Just similar, like what other inverse functions share these similar restrictions?
Cosine and cotangent.
Cosine and cotangent, right? Okay.
Yeah.
Now
It
for
doesn't
this
need to be
part,
the. Doesn't
it
need
just
to be
has
the
to be
exact same.
similar. Just has
Okay.
to be similar, right? And now we ask ourselves, is it easier to change secant into cosine or secant into cotangent?
Cosine.
Secant into cosine. Good. So we are going to choose the inverse cosine, and I'll show you how to get there. And we do this all by identities. Secant, what is the identity for secant? One over
1 over cosine.
cosine. And now solve this equation for cosine. This means multiply cosine to the right side. And you'll get 1 equals 3 cosine theta. And then divide by what?
Divide by 1.
Divide by 3, right? Because I said solve for cosine. And now what you're going to do to get to the inverse cosine is just apply the inverse to both sides. So this will become the inverse cosine of 1/3 equal to theta. And now I ask you to look at your calculator, and do you have an inverse cosine button?
I sure do.
Make sure you are in what mode?
Radian.
Good. Now type in the inverse cosine of 1/3, and what do you get?
1.23.
There you go.
So when you say identity, I thought identities was like, the sine squared plus cosine squared equals 1, or a bunch of
Yeah,
those
That's
squared
an identity
numbers.
too.
What if you get like a decimal radian value that's equivalent to pi over 2? You just have to memorize what the decimal value for pi over 2 is to make sure that it's
Oh, I
incorrect.
see what you're saying. Like, how do you know if it could be pi over 2?
Well, what if it's like equivalent to like what pi over? Oh, well, won't it become like a syntax error? No, it won't become a syntax error if the calculator is not paying attention to x is not equal to pi over 2.
Exactly.
It says right here it's 1.57.
Yes,
A bunch
but
of other.
say like you're given a
But you won't be able to get there because you can't be equal to pi over 2. Okay. So the whole point of this is you are creating a formula to calculate the value of secant every time you're given a value for secant. So what formula could be created? We could say that the inverse secant of x is equivalent to the inverse cosine of what? If we had 3, and then we converted it and it became 1 over 3, what could I write?
1 over x.
That's it. 1 over x.
And that is like straight up equivalent.
That's straight up equivalent.
So it will show up as an error in the calculator. Say, I'm gonna try it out.
Yeah, play around with it. Okay. So if you're ever given the inverse secant of any other number, then you know that you can always convert it to the inverse cosine of 1 over that number. Look at that.
That's cool.
We just created a formula. All right. And of course, maybe I can show it on Desmos. Let's see. This is always
Well,
in
so
ratios.
in my calculator, I did cosine or inverse cosine 1 over pi over 2, and it gave me 0.88068923.
Well, you did 1 over pi over 2, which means that's 2 over pi.
Yeah, but
So remember that those
If you-
are, and so the output couldn't be pi over 2. So that's what we're saying, right? Because it can't equal pi over 2. So remember that our output should always be a angle. So we're trying to avoid pi over 2.
Lewis, so if you type in inverse cosine of pi over 2, it gives you a domain error.
But the point was to type in 1 over x and say x was pi over 2, you know, or like the decimal value for pi over 2. Yeah, I'm gonna
What did I say earlier? Don't make it any harder than it is.
I need to understand.
Okay. So you
You
see
need
by
to take a
Desmos,
foundations of math class.
once you do, shoot a Caro, Lewis. All right. So here
Yeah.
you see by Desmos, the inverse secant of 3 is 1.23, and the inverse cosine of 1/3 share the same exact numerical value. Okay, so again, if you don't have a fancy calculator, this formula will save you, right? Okay. So next. So yeah, you can't type in pi over 2, but we'll get to that later. Because remember, it's a numerical value inside to return an angle.
Yeah, it'll just become 2 over pi.
Exactly.
Yeah.
All right. So let's go ahead and do the same with cosecant. You don't have an inverse cosecant button on your calculator. So we go ahead and make that conversion again. We say theta equals the inverse cosecant of -4. Then cosecant theta is equal to -4. On what restrictions?
0 to pi.
For cosecant?
Oh wait, no, for cosecant, negative pi over 2 to pi over 2, and you cannot equal 0.
Good. Okay. So we do this again. Which inverse trig functions share these same restrictions? Similar restrictions.
Sine?
Inverse sine. What else?
Tangent?
Tangent.
Inverse tangent. Is that
We're
it?
probably going to want to use sine, right? Because it's closest.
Exactly. So when we find these similar inverse functions, we want to know when we have this function, is it easier to turn it into sine or easier to turn it into tangent?
Let's do it the tangent way.
No. It's easier to turn it
Oh, right.
into sine, which means that you'd get 1 over sine theta equal to -4, and then just solve for sine, right? You get 1 equals -4 sine theta, which would give you -1/4 equal to sine theta. Then you would apply the inverse, and you'd get the inverse sine of -1/4 equal to theta. And again, does your calculator have an inverse sine button?
Yes. No, I'm kidding.
What
No.
is the value? What you got?
Negative 0.25.
Yeah.
Good, -0.25. There we go. Which means we have another formula. If you're ever given the inverse cosecant of x, you can rewrite it as the inverse sine of what?
1 over x.
1 over x.
So if it's ever one of these where it's just like the inverse of one of these identities, you can't type the calculator. All you literally got to do is just flip the inside.
Exactly. So now you can just use these formulas and it'll save you a lot of time.
Or we can get like super fancy calculators.
All right. You just use Desmos, right?
You got that money?
Oh, yeah.
Okay. So now let's try out cotangent. Ooh, man. Here's where we're going to get crazy, guys. Okay. All right. So we go through that same exact process. We'll say, I'm going to need the room on this one. There we go. So theta equals the inverse cotangent of 1/2. Then cotangent theta equals 1/2 on what restrictions?
That one was negative pi over 2 to pi over 2.
For cotangent?
No, 0 to pi. That's right. 0 to pi. And it cannot equal 0 or
Pi. So not included, right? Okay. Who shares these similar restrictions?
Cosine and secant.
Cosine and secant.
Oh, this one's
boy.
gonna suck.
Oh yeah. So
Super fun time.
I
Good.
would choose the easier looking function. So we're gonna go with
Cosine.
But in order to solve this one, in order to change cotangent into cosine, well, we're gonna have to use our unit circle. So this means that since they share the similar restrictions, here's what we're looking at. Here's 0 and here's pi. We know that pi over 2 is up there. If cotangent is positive, what quadrant am I in?
4 or 3 or 1.
Well, we only live in which quadrants?
Because cosine inverse is only.
We only live in quadrants 1
So
and
it's gonna be
2.
1.
Yeah.
So we have to be in 1. And if cotangent is 1/2, cotangent puts adjacent over opposite. So that means that this becomes 1, that becomes 2. And what's my hypotenuse?
Radical 5.
Radical 5. Okay. So now we are going to convert this to cosine. Oh, here's where it gets crazy, right? So we're going to say, I'll choose red. Why not? We're going to say, give me the cosine of theta. What's that going to be?
Square root of 5 over 5.
Square root of 5 over 5. And then we're going to apply the inverse. You get the inverse of cosine of square root 5 over 5. Now type that in your calculator.
Got
And
0.
I'll explain how everything works. What'd you get?
0. I
0.
probably typed something wrong.
Yeah, you definitely typed something in.
I got 1.1
1.1
or 1.11.
Good. You get 1.11. So the crazy reason why this works is because since they have similar restrictions, they're both positive in which quadrant?
1.
1. So the inverse cotangent of 1/2 and the inverse cosine of 1 over the square root of 5 or square root of 5 over 5 will share the same output. And I can show you that on Desmos because this has an inverse cotangent button. So if I said inverse cotangent of 1/2, do we get 1.1?
Yes, sir.
And if I say the inverse cosine of, I'll just put 1 over the square root of 5, we get the same numerical value. Oh boy. But guess what? You can't create a formula for that. So let me show you option 2. All right, method 2. All right, so we know that cotangent theta equals 1/2 on 0 to pi. Okay, well, if you think about reciprocal and identity functions, cotangent is the reciprocal function of what?
Tangent.
Cosine over sine.
Well, tangent.
Wait, no, I'm
reciprocal
sorry.
function.
Yeah, tangent.
So what we want to do is somehow fit the inverse tangent onto these restrictions. But we know that the inverse tangent lives from negative pi over 2 to pi over 2. Okay. So this means that we are going to take cotangent and we're going to change it into tangent. Okay. So, but before I do that, let me explain something. All right. So here is negative pi over 2. Here's 0. Here's pi over 2 and pi. The inverse tangent lives in quadrants 1 and 2. And cotangent lives in quadrants. Did I say 1 and 2? 1 and 4. And cotangent lives in quadrants 1 and 2. Which quadrant do cotangent and tangent share?
1.
They share quadrant 1. Good. So this means that they're going to have the exact same output in quadrant 1. So this means whatever our triangle would be and theta, they're going to have the same output. So now let's go ahead and change cotangent into tangent. So if I start back here, cotangent theta equals 1/2. Then you'd have cotangent, which is the same as 1 over tangent theta is equal to 1/2. All right. If you cross multiply, you get 2 equals tangent theta. And then apply the inverse, and you get the inverse tangent of 2 is equal to theta. All right. Now for some fun. Somebody type in the inverse tangent of 2 and tell me what it gives you.
Same. 1.11.
1.11. My goodness.
So this only works if cotangent or the inverse cotangent is positive?
Exactly.
Okay.
So if you wanted to write, now we can actually write a formula. So if we wanted to write a formula, we would say the inverse cotangent of x is equal to the inverse tangent of what?
X. Oh,
Well,
1 over x.
1 over x. But like you said, this can only happen if we're what?
If cotangent is positive.
Good. If our values of x are positive. Because if our values of x are positive, this means we are in what quadrant?
1.
1. Oh, yeah.
If it's negative, can you create a formula for that or no? You
That's
have
the
to do
next one.
Oh, okay. Cool.
So can you kind of combine these two methods?
What do you mean combine?
Like, okay, so you know how you found your quadrant in the first one by like using the unit circle? Can
Mhm.
you use that to find which quadrant you're in? But then when you set 1 over tangent equal to 1/2, can you do that for the second part? Because finding the way in method 2, the way you found the quadrants confused me a little more than how you just did it in quadrant 1 with the unit circle.
Yeah, don't mash them together. Either choose one method, but method 2 is way easier because remember that we chose the first quadrant because cotangent and tangent are both what in the first quadrant?
Positive.
Positive. So that's why we chose that. And it was the same explanation as the first method. We chose the first quadrant because cotangent and cosine are both what in the first quadrant?
Positive.
Positive. But if you do try to change it to cosine, then you have to use the unit circle, you have to complete the triangle, and then you have to find the inverse cosine. Method 2, well, if you have a positive x value, all you have to do now is just plug that into your calculator and you're done. So the reason I'm showing you these formulas is so you don't have to do this anymore. You just go straight to the formula and type it in. Make sense?
Yeah,
I'm trying to make your life easy, okay?
it does. I just need to get more practice with the quadrants.
All right. Now here is the trippy one. All right. Okay. So the inverse cotangent of -2. So we do the same thing again. Zoom in, give me the space, and we say theta equals the inverse cotangent of -2. Then cotangent theta equals -2 on those restrictions 0 to pi. Okay, well, we're going to go with a method 2 here and try to make a formula for tangent again. So we're going to try to make this into, we're going to try to make cotangent into tangent and see if we can put them on the same restrictions. -pi/2 to pi/2. Okay. So if I draw my unit circle, okay, here's -pi/2, here's 0, there's pi/2, and here's pi. If cotangent is negative, what quadrant are we in?
We're in 2.
2. So here's cotangent. I'll just say that here is cotangent theta because it's negative, right? All right. But once again, cotangent lives in quadrants 1 and 2. Tangent lives in quadrants 1 and
4.
4. So we have to figure out a way of how to get this angle into quadrant 4. How do we make it into tangent theta?
Like what reference or coterminal angles they're called?
No reference, no coterminal. How about the period of tangent and cotangent? When do they repeat
That's what
themselves?
I was thinking, which is pi, right? So
Good, because in quadrant, so if you think about it, in quadrant 2, cotangent's negative, and in quadrant 4, tangent is also what?
Negative.
Negative. And if they both repeat themselves every pi, that means if I took this
Yes.
angle and
Share
ended
the
up in
value.
quadrant 4, no matter what, you'd get the same output because they're both going to be what?
The same exact number. I mean, they share the same values.
They'll be the same values and they'll be negative. So all we have to do, let me erase that arrow, to get it from quadrant 2 to quadrant 4 is to take whatever value of theta we're given and add pi. Oh, it's a good time. So this means that if I go ahead and write this out, we're going to say that the inverse cotangent of x is equal to the inverse tangent of 1 over x plus what?
Pi.
Pi. There you go. But this can only happen if your values of x are what?
Negative.
Negative. Crazy, huh? So let's try it out. You're going to get the inverse cotangent of -2, and you're going to type in your calculator the inverse tangent of 1 over -2 plus pi. And tell me what we're going to get.
$2.68.
2.68.
I did it the regular way. That's why I already had the answer figured out.
Oh, you did it with method 1?
Yeah, using cosine as the
Nice. Yeah, and you can always resort back to that method. But again,
But I mean, that's just like so much easier, so much like less time consuming than what
well,
I
yeah,
did.
now that you have the formula, right?
Yeah.
Yeah. So again, just to show you, if I said the inverse cotangent of -2, we get 2.68. If I say the inverse tangent of -1/2, don't need that there, plus pi, we get 2.68. Crazy, right? So for you lucky kids, all you have to do is worry about this formula. If you know this formula, you just punch it in your calculator as such and move on. But that's how we create those. Any questions on that process? It's such a blast, right? It's mind-blowing.
Absolutely.
Mhm.
I mean, geez.
Yeah, my brain hurts.
Well, Ethan, just use the formulas and don't worry about anything else.
Yeah, the formula thing is so much simpler. I guess like saying it's just that whole
How to-
restrictions thing to
Yeah.
just to get to it. That kind of it's like, well,
Perfect. Okay. And if you have those fancy buttons on the calculator, again, lucky you.
Do you still want to see us do the work on the assignments?
No,
Even
you're
if we
good.
do have the fancy calculator? Not saying I'm gonna get one, but just asking.
For these ones, I mean, like I said, we created a formula for a reason. So, and I've been saying, hey, just plug it into the formula. So you really don't have to show any work on those ones.
Like,
Okay.
yeah, formulas are nice.
It's just rewarding, to make them.
I mean, yeah, I agree.
Okay.
Now that I know the formulas, I'm like, don't need to remake them. And that kind of sucks.
Exactly. Well, now you know how to remake them if you had to. Okay. So next up is write a trig expression as an algebraic expression. So this says write sine of the inverse tangent of u as an algebraic expression containing u. So remember what we did on the very first page?
Yeah, you substituted in.
That's what we're going to do here, except there's no numerical values. There's only a u. It's going to be the same exact thing. So we'll start off. We'll say let theta equal the inverse tangent of u. Then apply tangent to both sides, and you get tangent equals u on what interval? Where does the inverse tangent exist?
Negative pi over 2 to pi over 2.
Where x
Without
cannot equal
equal,
pi over 2 or negative pi over 2.
Yeah, not included, right? Okay, which means let's draw our unit circle just for the inverse tangent. There's negative pi over 2, there's 0, and there's pi over 2. If tangent is a positive u, what quadrant are we in?
1.
1. So there's theta. Okay, and now tangent theta equals u. And remember, tangent puts opposite over adjacent. So we're going to change u into a fraction. We're going to make it u over 1, which means the height of the triangle is u. The base is 1, which means what would my hypotenuse be?
The square root of u plus 1.
Good. Well, the square root of u squared. Did you say u squared or u?
No, I just said u.
Me?
U.
Me.
Wait, but why would you? Oh, because it stays squared until
Exactly,
an actual
right.
number gets put in.
It's conjoined by that plus sign, right?
There you go. Remember your radical properties. There you go. And there's your hypotenuse, which means that we come back to our substitution. And we now have the, well, first I'll rewrite it. Sine of the inverse tangent of u became the sine of theta. Now look at this triangle, and what is the value of sine at theta?
U over the square root of u squared plus 1, but then
Oh God.
you have to rationalize.
I don't think you have to. It might let you answer that, but if you did have to rationalize, what would you write?
U with the square root of u squared plus 1 over u squared plus 1. Or just u, right? Oh no, u squared plus 1 is a whole.
That's not as bad. It's also
Like,
It wasn't that bad. And there it is. That's what we did on the first page, but with more letters. And y'all, that is 8.2.
wait, can you explain to me why you wouldn't like divide the u from the u underneath and then just have the expression the square root of u squared plus 1 over u plus 1?
You tell me, can I actually reduce those?
I
That's
don't
a plus
know.
sign.
You didn't, so I don't know.
So can I actually reduce those two?
Well, my reasoning was kind of like yes at first, but then I looked at it and I'm thinking maybe not, because u squared plus 1 is an expression.
Not so much that it's an expression, it's what Ethan said. You can't cancel it because u squared is connected to the what?
To 1, or
To
like
1.
it's like its own. Well, what is it? What's it called?
It's if it's joined by multiplication, then you can do that stuff. But when
If
it's joined by addition or subtraction,
Oh,
can't-
because it's
you
adding
can't do
1
that.
to. Okay, no, I get it, because it's adding 1 to it, so it's different than what u is.
Exactly.
True.
So you
True.
couldn't do it. So If it's connected by addition or subtraction, you cannot cancel. What I like to say to stick in your head is that if it's connected by addition or subtraction, Red Rover cannot come over. They're holding hands.
Red Rover,
Think about it.
red rum.
All right. Well, that's 8.2, guys.